Say the word uranium, and most people instantly picture radiation signs, hazmat suits, and mushroom clouds. We have been conditioned to fear it. But long before it was loaded into reactors or weaponized, it was simply part of the Earth itself. If you held pure uranium in your hand, you would feel a surprisingly dense, incredibly heavy, and completely silent gray metal. How does a dormant mineral dug out of the dirt possess enough latent energy to run an entire metropolis, or erase one entirely? To answer that, we have to look past the modern anxieties and trace the history of what this rock actually is. In 1789, the German chemist Martin Heinrich Klaproth identified a new element inside a dark rock. He named it uranium, and for decades, scientists considered it a completely harmless decorative curiosity. Throughout the 19th century, manufacturers used uranium compounds to tint glassware and ceramics. As you can see in these vintage pieces, it produced an eerie yellow-green glow under the right light. That innocent era ended abruptly in 1896. French physicist Henri Becquerel was studying uranium salts and accidentally discovered they were emitting invisible rays strong enough to fog sealed photographic plates. That chance observation proved that this unexpectedly heavy metal was doing something previously thought impossible. Its atoms were naturally shedding energy. What makes natural uranium so active is actually a microscopic anomaly hidden deep inside it. Over 99% of a natural sample is an isotope called U-238, which is relatively stable. Mixed into that rock is a microscopic fraction, less than 1% of uranium-235. When a stray neutron strikes its fragile nucleus, it breaks apart. This fission releases heat and extra neutrons. These ricochet, striking neighboring nuclei, triggering a rapid, self-sustaining chain reaction. When that microscopic event repeats billions of times over, the cumulative energy output is staggering. A single fuel pellet the size of your fingertip can produce as much energy as a large volume of coal. That is the defining physical trait of the element, an extreme, almost unnatural concentration of power packed into a deceptively small space. To actually harness that power, human industry has to go to tremendous lengths. Extracting that rare fraction requires carving massive mining operations deep into the Earth's crust. Once the raw ore is pulled out of the ground, it undergoes heavy chemical treatment to concentrate the uranium into a bright, fine powder known as yellowcake. But yellowcake still contains mostly the stable isotope. To make it usable, facilities run it through a highly complex process called enrichment, which artificially filters out the heavier atoms to increase the density of U-235. Through this rigorous supply chain, a quiet mineral buried in stone transforms into a highly regulated strategic asset fiercely monitored by national governments. Once physicists figured out how to enrich the metal and control the chain reaction, the future of uranium split in two entirely different directions. Down one path lies controlled fission. Inside a nuclear power plant, the immense heat from splitting atoms boils water, creating steam to turn electrical turbines. This offers a method to produce massive, steady amounts of electricity for global infrastructure without relying on the continuous burning of fossil fuels. Down the other path lies sudden destruction. During the Manhattan Project in the 1940s, scientists packed highly enriched uranium into weapons, designed to let the chain reaction run wild, resulting in the devastation of Hiroshima. That absolute duality is why the metal remains so deeply unsettling. The exact same subatomic mechanism provides the ability to illuminate a city or erase one. Even when we choose the highly regulated path of generating electricity, utilizing this element comes with severe obligations. The industrial process leaves behind numerous hazards, ranging from contamination risks for mining communities to the controversial military use of incredibly dense, depleted uranium in armor-piercing ammunition. Then there is the issue of radioactive waste. The spent fuel remains hazardous far beyond the timelines of ordinary industry, demanding cautious oversight from generations that haven't even been born yet. Which brings us back to the quickest way to understand the reality of uranium. It is inherently neutral. A lump of heavy metal is not automatically a bomb, nor is it automatically a clean power plant. Materials do not make choices. People do. Uranium simply sits in the Earth, holding a mirror up to our own capacity for immense progress and catastrophic violence.